Hi everyone, hope you're well. We're going to look at the theory questions now for the higher level paper. So there's not a vast amount of choice they had in the theory. There's really, to get the 5 questions, I think it was quite prescriptive in that a lot of the paper was modern physics, which we're just starting into now. So don't get freaked if this sections you go, I've no idea. That's okay, you will. And we're exactly where we're going next. But for the max, we're kind of constrained, you only need a few choices. So if I were you, I'd have gone for the smorgasbord question, where they've a little bit from each one. The mechanics question, the optics question, there's a nice electricity question, question 10, and then question 14, B and D. Now, you wouldn't be able to get 100% because there's we've only tackled about 7 out of the required 8 of these from the smorgasbord question. There's 1 or 2 other bits here and there, but for the most part, if you chose your question carefully, there is a way to go. That being said, challenging paper, and let's get into it. Let's have a start. So I'm going to look at the smorgasbord question first. Question 6, always worth a look. Okay, so choose any 8 of the following. Each one's worth 7 marks. They're nice, brief, snappy, short questions. Okay, so let's look. State the principle of conservation of momentum. Just move this across here so you can see what I'm doing. The momentum before collision in the system is going to be equal to the momentum afterwards. So you could give the equation as long as you annotate it. So m1u1 plus m2u2 is equal to m1v1 plus m2v2. As long as you specify, m1 and m2 are the masses of the 2 objects involved, u1 and u2 are the initial velocities, and v1 and v2 are the final. So principle of conservation of momentum, that wherever momentum is in the system beforehand has to be there afterwards. Be that positive, 0, or negative, depending on the direction you've chosen. So, part B. The pressure due to the ocean is 3.72 by 10 to the 7 pascals at the position of the sunken RMS Titanic. Calculate the depth of the Titanic. Well, this comes down to the pressure at depth in fluid is equal to the density of the fluid times the acceleration due to gravity times the depth that you're at. Now, just to draw your attention for a second, say due to the ocean, so you can disregard the atmosphere. Okay, we're not worried about the fact that even though they're at the bottom of the sea, you've got the pressure from the water. Sometimes there might be a more tricky theory question where you have to take into account the pressure from the atmosphere as well. That's not the case this time. It's just the pressure from the water. So it's just density times acceleration due to gravity times h. So this time we're looking for the depth. We know the pressure, we know the density, we know the gravity, acceleration due to gravity. So just rearrange it. The depth is the pressure divided by the density of water times the acceleration due to gravity. So when you work that out, you get a depth of 3,795 meters. So about 4 kilometers down. That makes sense. It's a common sense check. Does check out. Excuse me. So part C, a little trickier. And we've talked about simple harmonic motion recently, but we haven't really consolidated it too much. So let's look. An object is executing simple harmonic motion at an acceleration of 3.78 meters per second squared. Calculate the period of the object when it is 55 centimeters from the equilibrium position. Okay, so if in doubt, first just go and find the simple harmonic motion section of your log tables, which is page 54. And there's a couple of equations I've just taken out from here, that the acceleration is equal to minus omega squared times the displacement, and the time period is 1 over f, 1 over the frequency, which is equal to 2 pi over that omega. Rearranging this for slightly, let's get what w squared is. Excuse me. Which is the acceleration divided by the displacement. Ignore the minus sign for now. That's just telling us that the acceleration's against whatever direction you've displaced something. So if this is the pendulum and you displace it this way, that the acceleration is trying to go back into its original position. So you can ignore the minus sign. So that gives us, if we're looking for w squared, from which we can get just what is w. So I keep saying w, the omega. So omega squared is acceleration divided by displacement. Got to be careful here. The 0.55, they give it to you in centimeters. You remember always meters here. So that gives us 6.872 seconds to the minus 2. And the time period is 2 pi divided by this. The time period is what we're looking for. So 2 pi divided by the square root of that gives us 2.3967 seconds. Look, I know we've covered this, but we haven't really tackled too many of those questions. So I'd revise the simple harmonic motion chapter and just look at some of the questions. We'll be doing it again, but just if you're not comfortable with what just happened there. Okay, back onto firmer ground. State the thermometric property of a mercury thermometer and a thermometer based on thermistor. So for mercury thermometer, it's the length of the column of mercury, as long as it's a uniform cross-sectional area. So that when I say uniform cross section area, so if it's a cylinder, it's a cylinder, it's a circle the whole way up, or if it's a square, it's a square the whole way up. So that the increase you see, the length is corresponds to the volume. So as the liquid expands, it goes up. Second one for a thermistor, it's electrical resistance. That's the thermometric property of the thermistor is based off. Nice, short, punchy questions. Let's keep moving. Part G, a little bit more involved. How far from a charge of 16 microcoulombs will the electric field strength be equal to 9 by 10 to the 5 newtons per coulomb? Okay, so go to your log tables, get the, let's go to the Coulomb's law bit. Where are we at? I should be giving you page numbers as we go here, guys, just to help. There we go. Coulomb's law and electric field strength, page 61. So the electric field strength is the force of attraction or repulsion between the two charges divided by Q. And this Coulomb's law is the force of attraction between them. So if you divide this equation by Q, you end up with just one of those Q's on top, which is what we got here. So electric field strength is 1 over 4 pi times the permittivity free space multiplied by the charge and divided by the square of the distance. Again, log tables being your best buddy, we need the permittivity free space. We need that EI. So there is a page of important constants on page 46. So things like the speed of light, the mass of an electron, all this kind of jazz, the Newton's gravitational constant, which I think is going to come back to haunt us later on. But we're looking for a permittivity free space. There we go, boom, page 47, 8.854 by 10 to the minus 12 farad per meters. So yeah, plugging them in. We're looking for the distance at which we get this electric field strength. So let's just rearrange it. The electric field strength is 1 over 4 pi permittivity multiplied by the charge of the particle divided by the square of the distance. So we'll just do a little bit of algebra. Bring the d squared across, the e across. D squared is equal to the charge divided by 4 pi permittivity free space times the field strength. And then we're looking for the distance, so we're going to get the square root because this is the distance squared, so square root of both sides. Plug in the numbers, 16 microcoulombs, that's by 10 to the minus 6, divided by permittivity free space, the electric field strength, and that gives us a distance of 0.3998 meters, around 40 centimeters. Excuse me, a bit more of a workout for that one in fairness. Okay, part H, explain the principle by which optical fibers transmit signals. Well, the name of it is total internal reflection, but they say explain. They want a bit more detail. So always add in a diagram here, always helps. There's my optical fiber. There's my ray of light. I really should be drawing in some normals here and some angles of incidence, angles of reflection, and just, it works in the process of, on the principle of total internal reflection. That if the angle of incidence is greater than the critical angle, you'll get the light return, as you go from a denser into a less dense medium, you get total internal reflection. So that's the principle by which the optical fiber works out. Okay, part I, sketch the IV current against voltage graph for an electric light with inactive electrodes and a vacuum. Okay, so again, this is where we're hitting on the second part. It's stuff we haven't really talked about yet, but let's look at the first one. So inert electrodes. If they were active electrodes, you get a straight up IV, but because they're inert, they need a little bit of juice to get moving. So you have the current increases after you pass a certain amount of voltage, once you get the chemicals kind of moving in the electrolysis. Okay, the thermionic emission. This is one section we haven't really gone on to yet. In a vacuum, if you heat a cathode enough, like if you heat a block of metal enough, you can give the electrons enough energy to escape from the metal. And this is called thermionic emission. We'll be going on to it as soon as we're back, pretty soon after we're back after the half term. But this is the IV graph we're going to get. This is he not having put in IV. Where you get an increase and then eventually you reach a point where it's maxed out and you've gotten rid of all the electrons, so to speak, or the free ones. Okay, that was the smorgasbord question. You wouldn't have been able to get the full whack, but a good 80-90% of them anyway. Let's keep moving. Okay, so again, you didn't have a vast amount of choice on this test, so I'm going to follow the list of what I think was most likely that you tried. So question 7, the mechanics one. This is about kinetic potential energy and a few ways to tackle it. So I think I've tried to go for the most straightforward one. Distinguish between kinetic and potential energy. Well, potential energy is the energy an object has due to its position in a field. So like a gravitational field, an electric field, etc. Or you can store elastic energy. That's potential energy. Stored energy that could be released, or is the energy something has based on where it is in a field. Excuse me. Whereas kinetic energy is the energy something has that it's moving. Actually, in the formula, why not? Okay. Show using the equations of motion or otherwise how potential energy is converted to kinetic energy for an object after falling from rest through a height of h. Um, I've gone with otherwise here. So instead of the equations of motion, I'm not quite sure. This is one of those times where I would like to have a look at the mark scheme and see I'm not leading down the garden path here. But I've just gone with just equating them. That if something's falling, it's going to lose gravitational potential energy and gain kinetic. So the loss of gravitational potential, mgh, versus the gain in kinetic, half mv squared. So you just equate them, and we're looking for the energy gained as it goes through a certain distance. So get rid of mass from both sides and bring the g across, the acceleration due to gravity. The height is equal to the velocity squared divided by 2 times the acceleration due to gravity. Not quite sure. I might be off there, guys. I'll have to have a rethink about that one, but I think that's what they're looking for there for part 2. Okay, on to the more kind of an application of it. A copper ball of mass 5 kilograms is released from the top of a smooth slope, excuse me, of length 10 meters and slope angle 45 degrees. Calculate the acceleration of the ball as it rolls down the slope. Okay, so this is a vector question, really. Resolving vectors into their components, at least at first. So you've got a downward acceleration of 9.8 meters per second squared. But we're not going to get that full whack because it's at an angle of 45 degrees. Now, your temptation straight away is to think, 45 degrees, well, that's half of 90. That's just half the 9.8. Not going to work. What you're looking for is we're looking for the component of gravity which is going to act parallel to the slope. And that's given by the sine of the angle times the magnitude of the vertical vector we're looking for, the 9.8. So it's times gravity. So sine 45 times 9.8 gives us an acceleration due to gravity of 6.9296 meters per second squared. Calculate the acceleration as it rolls down the slope. Okay, so calculate the velocity of the ball when it reaches B. So we're onto some Suvat stuff here. So we have, let's think just going in this direction. The displacement's 10 meters. Initial velocity is 0. We're looking for the final velocity, and we have an acceleration of 6.9296. So here's the standard motion equations for your logbooks. We're looking for ones that something that has an S, a U, a V, and an A in it. I think it's going to be this guy right here. V squared is equal to U squared plus 2AS. Get the square root of both sides. Because U is 0 here, because it's starting off from rest, this U squared just kind of goes away because 0 squared is 0. So the velocity is the square root of twice the acceleration times the displacement. So twice the acceleration we got from part 1 times the 10 meters gives us a velocity of 11.77 meters per second. So that's the velocity of the ball when it reaches B. It's going 11.77, like so. Okay. Excuse me. Assuming that all the energy converted from friction is absorbed as heat by the... Oh, sorry, I beg your pardon, I skipped a bit. Calculate the velocity of the ball when it reaches C. Okay. So, presuming that we've got an initial velocity of 11.77 meters per second, I'm wondering now, should we have broken that down also into 135? I'm going to go off this, guys. I could be wrong here. I'll hold my hands up if I am. But I'm going to go with an initial velocity of 11.77 meters per second, so at point B. So it's rolling down the hill. It's picked up to a velocity of 11.77, so that's an initial velocity. And it's going to lose some speed. It's going to decelerate as it goes between B and C because of friction. I skipped this a little bit here. Look at this. The ball then continues along a rough horizontal surface where the resistance force is 15 newtons. Okay, so now that we know that, after having read the question, which I'm always telling you guys to do, we're looking for the acceleration that this force causes. So F equals ma. The acceleration is the force divided by the mass. 50 newtons divided by 5 kilos gives us a deceleration of 3 meters per second squared. Now, the whole positive negative vibe, okay? Because if we're going with this direction being positive, which I know is kind of counterintuitive because we read from left to right, but as the ball is rolling in this direction, it's going 11.77 meters per second. The acceleration is trying to slow it down, so it's going in the opposite direction, so it has to be negative. So whatever system you use, they're going to be opposite signs here, that's what I'm saying. So, with an acceleration of minus 3 meters per second squared, we have our initial velocity and we have our displacement. Again, I think v squared equals u squared plus 2s is our winner here to get the final velocity. So just plug in the numbers. To use the square root of this time, to be careful because the u is not 0, so the u does not go away. 11.77 squared plus 2 multiplied by the minus 3, because that's the minus negative acceleration times the 10, gives us 8.862 meters per second. Quick point, you might notice I've left out my units in the middle of the calculation. That's absolutely fine, but you have to include them at the end. Okay, make sure you include your units at the end or you're throwing away a point, and those points add up. Excuse me. So that's part V. Part VI. Assuming that all the energy converted from the friction is absorbed as heat by the ball, calculate the rise in temperature of the ball as it travels from B to C. Okay, so we're presuming that all of the lost kinetic energy is equal to the heat that's going to be produced by friction. So the change in kinetic energy is half the mass times the different, the velocity, initial velocity squared minus final velocity squared is equal to, from the temperature side of things, whatever energy is put in to get the change in temperature, mass times the heat capacity times the change in temperature. So we can eliminate mass from both sides here. The mass kind of doesn't really become relevant because it's on both sides of the equation. So half v squared minus half of the final minus, the change in velocity, the change in kinetic energy, beg your pardon, divided by the heat capacity. Plug in the numbers, half, 11.77, that was our initial velocity squared, minus half of 8.862. This gives us the change divided by the heat capacity of copper, which is, I think the ball is made from copper, gives us 0.0769 Kelvin, or 0.0769 degrees Celsius, because it's a change in temperature we're looking for here, and that's the change. Okay, I think there's a heat question coming down the line, so I don't need to labour the point about Kelvin and Celsius not being the same, but them being the same interval. Okay, what else have we got here? Now, we're on to a bit that you might not have been comfortable with, especially the second part. The ball then travels up a smooth circular surface of a radius 5 meters. Calculate the maximum height. Okay, this is another energy one. If the kinetic energy of the ball, if all of that was converted into gravitational potential energy as it goes up, then the change in gravitational potential energy is equal to the change, the loss of its kinetic energy. It'll again eliminate mass from both sides and bring the g across. So we have the maximum height it reached is v squared over 2g. When I say remember me, that's because if you look back at part 2, that's what they wanted us to do, to get to this kind of equation here. So the height is v squared over 2g. The velocity that it had just before going into that, curvy bit, so just before it goes into the quarter circle, is 8.862 meters per second. So square that, divided by 2 times g, and you get a maximum height of 4.007 meters, which again, do a quick common sense check. If you ended up with like 4 kilometers or something, or 1 centimeter, then you know it's going wobbly. But 4 meters seemed a bit reasonable. Didn't quite make it all the way to the top of the slope, but got most of the way there. Now, this bit you would not really be able for, I think, unless you went back and revised circular motion, which we just scratched the surface of. We have to go back to hit. Calculate the maximum centripetal force experienced by the ball as it travels along the circular surface. So the centripetal force, F equals mv squared over r. The mass of the ball this time is relevant. It's 5 kgs times its linear velocity divided by the radius gives us 78.5 newtons. And again, you might not have been able to access that last part, but the vast majority of it, hopefully, should be sensible enough. Okay. That was the mechanics question. Onto the optics one, which I think, just move this out of the way for a sec. So, excuse me, the diverging lens. So in a diverging lens, the image is always virtual. The image form is always virtual. What is meant by a virtual image? Well, a virtual image is one where the rays of light look like they intersect, but they actually don't, and you can't project that image onto a screen. State 2 are the properties the image produced by a diverging lens will always have. It's always going to be diminished, and it's always going to be upright. At what distance? Draw a ray diagram to show the image formed by a diverging lens. Okay, so you got your object, your diverging lens. For this one, it doesn't matter if we're inside or outside the focal point, because our image is always going to be virtual. Couple of things. Whenever you're asked to get an image, you're going to need 2 rays of light. So there's my first ray of light going through the diverging lens and emerging as though it had come from the focal point on this side. And the other one, you can go straight through the optical center And then you backtrack this one to see where they intersect, and there's your image. There's our diminished upright virtual image V. Okay, bit of calculation I think for part 4. Excuse me. At what distance from a diverging lens of focal length 30 centimeters should an object be placed so that the image formed is 1/3 the size of the object? Okay, so a bit tricky because at first you're used to using the lens equation, right? And I'd say most of you would have gone, okay, 1 over f equals 1 over u plus 1 over v. You'd found that. And you probably remembered that we're using the virtual image, so it's minus 1 over v. And if you remembered, because it's a convex mirror, or sorry, a convex convex mirror, using minus 1 over f. So you'd have been able to get to here. 1 over u minus 1 over v is minus 1 over f. But then it kind of looks like we're missing information in that we have the focal length and we have not much else. We don't have u or v. But what we do have is the magnification. If the magnification, which is v over u, is equal to 1/3, now I'm not plucking these out of thin air, guys, I'm just show you where I'm getting these from the log tables. Excuse me. Here we go. So there's the mirror lens formula on page 60, and there's the magnification formula right underneath it, also on page 60. We're going to need these other two in a moment, so I'm going to keep this to hand. Okay, so we do know the magnification, which is v over u, which is equal to 1/3, so we can get either v or u here by a little bit of algebra. So v is equal to u over 3. We're going to get that because we're looking for u. So if I sub v in, I'll be left with some variation of u's to solve. So this formula, 1 over u minus 1 over v equals minus 1 over f, becomes 1 over u minus 1 over, and now that we know v is u over 3, I sub that in, is equal to minus 1, and f is 30 centimeters. I'm not going to get too hung up on meters, centimeters now, as long as we remember we're talking centimeters. So that means that this fraction here, 1 divided by u over 3 is the same as saying 3 over u. 1 over u minus 3 over u is equal to minus 1 over 30. It says minus 2 over u is equal to minus 1 over 30. The minuses cancel each other out. U is equal to 60 centimeters across multiplying. So the original question is what distance should the image be? And that's at 60 centimeters. Yeah, we're not looking for v, but we may as well do it just real quick. As m equals v over u, and we know that v is 60, you can plug that in and you can get v, the distance of the image is 20 centimeters. Excuse me. Okay, we're on to part v here, which is what is the diameter of the sphere if an image of the same size as that produced by the lens is formed? Okay, well, you could go back and do what I did, which was a bit of not a lost cause, but a lost time here, which is use the lens equation again. 1 over u minus 1 over v equals minus 1 over f. And we're using the same, because we're using the same u and v that we just gotten, we should get that the required focal length is also 30 centimeters. Again, I reserve the right to be wrong here because this seems too easy to me, but it is what it is. So if the focal length is also 30 centimeters, we just got to be a little bit careful because this time they're asking for the diameter of this sphere. So remember that for the spherical mirrors, the focal point is halfway between the center of curvature and the radius. So if we're looking for the diameter, it's 4 times that. So if the focal length of our sphere is 30 centimeters, the diameter should be 120 centimeters to make this happen. Okay, not an easy optics question in fairness, and I'm not sure if there's an easier way to do that one. Let's have a quick look. So the eye, stated defect of the eye that can be corrected using a diverging lens, that's short-sightedness, when the image is formed inside the ball of the eye and you want it to be on the retina. So you want to spread it out a bit more. VII, the focal length, Captain, of the cornea lens combination in an eye should be 1.5. So the power of your eye should be 1.5 centimeters. The focal length should be 1.5 centimeters when you're looking at a distant object. So here we're going to use the power equation. So the power of a lens is 1 over the focal length. Remember, we're talking about like the bendier the lens, the more powerful it is. So the shorter the focal length, the more powerful the lens. And a combination of lenses, you just add the powers together. So we should have a power of 1 over 0.015. Got to be careful. This time we need to get the focal length in meters, okay? So 1 over 0.015 plus 1 over the focal length that we're looking for, of whatever the lens we're going to need for this person to have better eyes, is 1 over 0.014. because this is their actual power of their eye. So it's not quite powerful enough. So 1 over f, the focal point of the lens we're looking for, is 1 over 0.014 minus 1 over 0.015. Plug it into your calculator, you get 1 over f is 100 over 21, cross multiply, you get 100 f is 21, f is 21 over 100, or 0.21. I remember we're talking about meters, so we need one that has, you can either leave it in meters for the focal length, or change it to centimeters, but the minus sign here is important, okay? I omitted it here, actually. So 1 over, this is going to be minus. Is it going to be minus? Let's just check something here real quick, guys, because 1 divided by 0.014 minus 1 divided by 0.015 bracket. It's not minus. Aha, I'm wrong. Sorry about that. It's a converging lens we need. For some reason, I imagined this minus. Let's pretend I didn't. Again, that's one of those reserve the right to make mistakes thing. So we need a converging lens with a focal length of 21 centimeters. Excuse me. Or there's the optics question. Sorry, I'm running out of steam a little bit. You can probably sense I'm making more mistakes. I'm getting a little bit more verbose, so I'll try and keep it a bit snappier for question 10. Our question 10 is a electricity transmission question about transformers and power and stuff. There'll be one part here that you wouldn't be able to do, the define the unit of electrical current, but let's do the rest, because the rest is accessible. That's going to be like 3, maybe 6 marks out of the 56, so let's get the rest of them anyway. So, explain what is meant by alternating current. That's when the current reverses direction many times per second. This is the bit you might not have been able to get. So when they say define the unit of electricity, I know that 1 amp is 1 coulomb of charge flowing per second, but that's probably not what they're looking for. They're looking for, and this is from the F equals ILB stuff, the electromagnetic induction and interaction that we talked about fairly recently. So 1 amp will be the current that gives 2 wires that are 1 meter apart, a force of 2 by 10 to the minus 7 newtons per meter. It's one of these rare bits of you just have to memorize this thing. It's tucked away towards the back of the book, of your textbook. It comes up every now and again, but it is an awkward fella, and there it is. Okay, 3. Explain why EHT voltage and AC are used to transmit electricity over large distances. Okay, so if you're transmitting electricity over large distances, you want to get as much of that energy to your destination as possible. You don't want to lose it as heat. So Joule's law states that the energy you lose as heat is proportional to the square of the current. It is equal to the square of the current times the resistance. But the upshot here is the square of the current thing. So if you want to reduce the amount of heat you're losing, you really want to bring that current down, because it's going to be square, that's going to be your heat loss. So the heat loss to the environment is proportional to the square of the current. So why do we use high voltage? Because as power is equal to current times voltage, if you increase the current, you decrease the voltage and vice versa. And we're looking to decrease the current. So if you've got a high voltage, you're going to have a low current, which means you're going to lose less heat. So that's the first reason. Secondly, as for AC, it's because it is a less heating effect than the DC of the same voltage. Because if you remember that sine wave thing, it's always going to be, it's not always going to be at the maximum of its value. Most of the time it's going to be less than that. So you get less of a loss as heat for AC. Okay, that's parts 1, 2, and 3. Now we've got a diagram of the electricity distribution network for a country. We've got generation stations, transmission lines that bring that power to a transmission substation, sub-transmission lines that bring it to a distribution substation. So just to put this in a more of a local context, this would be like at the top of the road as you go to the school and turn right, there's your transmission substation. And these distribution substations, they're usually in these really small boxes in the States, the ones that have high voltage signs on, and they tell you not to sit on. That's why. And people always sit on them. And then you've got a distribution line that brings it to the actual customers in the houses themselves. Excuse me. So, a generating station produces electricity at 25 kilovolts and 11,200 amps, which is converted to blah, blah, blah. We'll come to that in a minute. Calculate the power produced by the generating station. Well, all that matters for power is its current times voltage, which is 11,200 amps times 25,000 volts, which is 280 million watts or 280 megawatts. Both absolutely fine. That's part IV. Calculate the current flowing the wires when the electricity is being transmitted with a voltage of 400 kilovolts. So presuming that we don't lose any power, and we have this power of 280 million watts, this time we're looking for the current, so it's power divided by the voltage, which is 400 kilovolts, which works out as being 700 amps. So that's for there. And now we're on to the transformer. Okay, so a transformer transforms electricity from high voltage, low current to high voltage, low current to low voltage, high. Okay. Let me try that again. It converts electricity from high current, low voltage to low current, high voltage, or vice versa, depending on what you're trying to do. So this time, before entering individual houses, this is going to be a step down transformer. You want to get it from high voltage into low voltage with a higher current. The voltage and current input to the last transformer is 7200 volts and 1.1 amps respectively. Okay, so let's just see what we got here. Calculate the output current from the transformer. Okay, so first off, let's look at the input power. The input power is voltage times current. 7200 times 1.1 is 7920 volts. Watts. However, we lose 10% of that. So whatever that voltage was, we're only going to get 90% of it as output. So we got 7128 watts as output. Now, that's the output power, but they're asking us for the current. So we need to divide the power by the voltage that we're given of 230 volts, which gives us 30.99 amps. That's the output current. I hope I didn't do that too fast there. So what did we do? We got our input current, our input power, which was the voltage times current. We took into account the fact that we lose 10% of that to get our output power. And then we're given that the output power needs to be at 230 volts. So as power is equal to voltage times current, and we're looking for current, you divide the power by the voltage to get the current, which gives us 30.99 amps, which is still like a huge amount. Okay, so that's part 6. Part 7, which I forgot to label here. Calculate the number of turns in the primary coil if there are 150 turns on the secondary coil. Okay, so VI over VO is equal to NP over NS. This is from your log tables, page 62. So the input versus output voltage, primary and secondary coils, where primary is the first, secondary is the second. So 7200 volts over 230 volts, that's incoming voltage over outgoing voltage is equal to the number of turns of the primary, which is what we're looking for, divided by 150, which is the turns on the secondary. So just bring that across, multiply it out, and you get 4,695.6 turns. And that's disregarding the energy loss. That's presuming that we're going for this 7,200 volts versus 230, as opposed to like 90% of that. So that's 4695. If we do have to take into account the energy loss, which I'll check again the marketing, works is slightly more turns, 5,217. But I couldn't be certain on that. Okay, we're almost there for this question. And for this video, I'd say, because I'm running out of steam anyway. Excuse me, last part, calculate the peak current entering the house. Well, this is again from your logbook. The IRMS, the root mean squared, is peak divided by root 2. Now we're looking for peak, so let's just bring that root 2 across. So the peak current is the RMS, which we've just calculated, times root 2. So it's 30.99 times root 2, which is 43.82 amps. That's the peak of the AC that you'll get. Okay, and again, if you're wondering where I plucked that fella from, same page, 62. Boom, there we go. Okay, last question. So just to kind of have a look here, 11 is light, 12 is modern physics, so is 13, that's atom and radioactivity, which we're going to next. Now we're on to question 14. This first one you might have been able to have a shot at, angular velocity, but there's a good bit of circular motion creeping in. Might be a little bit tricky, but it's doable. But I've opted for B and D instead, so let's have a look at them. I'm more than happy to go through that in class as well. If like for A, we'll be going back onto circular motion soon enough. But let's do B and D first. So for B, a heat pump uses technology similar, blah, blah, blah. What is latent heat? So latent heat is the energy needed to cause something to change state without changing its temperature. Now, they don't ask specific latent heat, but just in case, here's the answer, specific latent heat. Specific latent heat is the heat needed to change the state of 1 kilo of a substance without changing its temperature. So remember, that's when all the energy is being hidden, that's where the latent part comes from, into changing its state. Now, explain with the aid of a label diagram how a heat pump works. This is going to be the bulk of these 18 points. So there's the diagram. You got the thing you're trying to cool with a tube for coolants to go through, the coolant fluid. You've got an expansion valve and a com- compression valve. So what happens is, first, you can start from any point in the cycle, but I find it easier to start here at the expansion valve. So cooling fluid, low boiling point, and a high latent diffusion of heat is used. So low boiling point because you want it to turn to a gas without, it needing to be at a high temperature, because you want to keep the whole thing at a cool temperature. And the high latent heat diffusion, we want it to store as much energy as possible. So not store, to use as much energy as possible to become a gas, and then shed as much here. So we want a high latent heat of that should be vaporization. High latent heat of vaporization. Sorry about that, guys. So we need a fluid which has a low boiling point so that it boils at low temperatures, and a high latent heat of vaporization so that it will give out a lot of energy when it condenses back into being a liquid out here. So I'm getting ahead of myself. That's the fluid we use. As it goes into the expansion valve, it goes into a low pressure zone, which allows the fluid to vaporize very easily, and it will take the heat it needs to do that. It will take from the contents of the fridge or the car or whatever you're trying to cool, which turns it into a gas. Then when it hits the compression valve on the outside of the fridge or car, it's going to be compressed, forcing it back into being a liquid, and it has to shed that heat, which it releases then into the outside world. So that's the principal operation of a heat pump. The last one is a little calculation, mini heat calculation, with a bit of a twist on it, because this is higher level, this is what they do. R290 propane is a circulating liquid commonly used in heat pumps. Calculate the amount of heat extracted by a heat pump in an hour if 150 grams of this propane circulates once every 6 seconds. Okay, so first off, let's figure out how many times it goes through the whole circuit. If it takes 6 seconds to do one circuit and we've got an hour, well, it's going to go through 600 times, because 1 hour by 60 minutes by 60 seconds gives us we divide that by 6. It's going to go around the cycle 600 times. So we can do this a number of ways. You could do just 150 grams then times by 600, but I think it's easier. Let's imagine that as being the equivalent of 600 times 150 grams. So 600 times 150 grams is 90,000 grams that have gone around through the cycle, or 90 kilos. So what we're really looking at is how much heat does it take to evaporate 90 kilograms of the substance. The heat needed is the mass times the latent heat. The mass is 90 kgs, and the latent heat from the question is 4.256 by 10 to the 5 joules, which means that in 1 hour of operation, it will remove this amount of joules, 38 million joules and some change. All right, guys, I think I stopped making sense somewhere there in the middle, but hopefully this was useful. I'm more than happy to look at some of this question with you guys as well. There's a couple of bits there that might be tricky, but it's really down to using G is equal acceleration to gravity is gravitation constant times mass divided by the radius squared. That's the fella. If you try this and you want me to go through it, let me know. Otherwise, I might do it as a little addendum video and I'll do it in a moment. But for now, I'm going to cut it short there. Hopefully this made sense and was useful, and I'll talk to you soon.